In module 7.1, we were talking about identifying whether a function is increasing or decreasing, finding any local extrema. In module 7.2, now what we want to do is talk about the concavity of a function. So the idea here is going to be similar to how we went about identifying intervals of increase and decrease. The difference, though, is going to be that we're going to be looking at the second derivative of a given function. So to start getting this idea across, let's consider a function that passes through the points -5, -3, and 5, 3. So assuming that we look at a sign chart for the first derivative of a given function, and we know that on this entire interval, our function is increasing, which makes sense if we're at -5, -3. To get to 5, 3, at least somewhere in there we have to be increasing. So the question becomes, if we know that our function is increasing to get from this first point to the second point, how is it curving to get to that second point? So for instance, I could draw a graph that's increasing from the first value to the second value. So that curve passes from -5, -3 to 5, 3, and it's increasing. I could draw another curve that passes from -5, -3 to 5, 3, and is also increasing. So just knowing that our function is increasing isn't enough to know, does our function curve upward? Does it curve downward? Essentially, what path or what type of direction does it head to get from one point to the next? So increasing, decreasing is part of the question that we need to understand in terms of understanding the behavior of our graph. The other thing that we need to consider is the concavity of our graph. And concavity describes the way that a function curves from one point to the next. So a function can be concave up, or it can be a curve that opens upward. If we have something that looks like this. So this curve opens upward, so we would call that concave up. And if we were to look at a sign chart for, in this case, the second derivative of our function, we would see that the second derivative is negative. I'm sorry. If we look at the first derivative of our function, let's not jump ahead to the second derivative yet. If we look at the first derivative of our function, we have a critical value. We see that our function is decreasing and changing to increasing. So a curve that's concave up can either be decreasing or increasing. So it's not about whether our function is increasing or decreasing, it's about the direction of the curve. So we can have a curve that's concave up, or we can have a curve that's concave down. Or another way to say that is a curve that opens downward. So an example of that would be a curve like this. So in this case, our curve is opening downward. And if we looked at the first derivative of our function, again, we'd have a critical value, and our function would be increasing for part of that curve, decreasing for the other part of the curve, but the entire time it's concave down. One method for trying to understand this idea of concave up or concave down would be to imagine if this is a bowl and trying to pour water into it. So if we poured water on this graph, all of that water would collect inside this bowl. So that's concave up. If we poured water on this second graph, all of it would hit and just run down the side, so it wouldn't catch or collect anything that was poured into it. And that's the idea of concave down. So either a bowl turned right side up or a bowl turned upside down. So we can determine the concavity of our function by constructing a sign chart for the second derivative of our function, which we denote as f double prime of x. So instead of the 1 tick mark there, we've got 2 to indicate what we want as the second derivative. If our second derivative is greater than 0, then the function is concave up. If the second derivative is less than 0, then our function f of x is concave down.